Hi and welcome again to my physics online video lecture series. Today's video we're going to be talking a bit about interferometers, and I'm going to talk a little bit about the principles of interferometers in general, and then I'm going to focus a bit on the particulars of the Michelson interferometer. Okay, interferometers in general basically involve splitting a beam into two pieces and then sort of rejoining that beam some time and distance later. So that's the key technology or the key component to interferometers is what's called a beam splitter. We often label it as BS in the drawings for beam splitter. You also typically need to have a couple of mirrors, which we usually label as M. Beam splitters, there's a variety of ways of basically splitting a beam. The predominant way, and this is the one that we're going to consider in here, would be to basically take a mirror and partially mirror it. It's just like putting partial silvering on it. So it reflects a part of the beam, it transmits another part of the beam. Okay, and so essentially what that would look like in a diagram, you have, typically you draw it like this for your diagrams. You might label it BS or beam splitter or whatever. Your laser comes in. This is your incident beam of light intensity. Some part of it gets reflected, so this is your reflected, and then this right here is the transmitted beam. Now, energy conservation says that the incident must be equal to the reflected plus the transmitted. They're often labeled by fraction transmitted versus fraction reflected. And so that means that you may be labeling your beam splitter as, say, like 60-40. And a 60-40 would essentially mean 60% is reflected and 40% is transmitted. You could also have a 40-60, so just reverse the numbers. You could have an 80-20, you could have a 70-30. The most common one for our purposes would be a 50-50. So 50-50 beam splitter would basically mean that the R and T components are each half, so 0.50 times the incident intensity. Now there is often a little bit of loss as well, so it may really be more like 49%, 49%, and 2% is just scattered or otherwise lost. Okay, so what are some basic beam interferometer designs? So one of them would look basically like this. All of them essentially involve splitting your beam in some way and then recombining it later. So one version might look like this. I have a beam splitter, send my laser in, part of it's reflected, part of it's transmitted, and then essentially what I would do is put a mirror and then put a mirror. Okay, so this is M1, this is M2, this is beam splitter 1. Okay, so now this is heading off this way, and then I'm going to put another beam splitter right here. And this beam splitter could be, for example, like this. And so now this beam hits and this beam hits, and it can either come out this way or come out this way. And what determines which way it goes is basically how much phase does this have relative to this. And so when they are when the phase difference is, say, 0, then all of it will go one way. When the phase difference is pi, all of it will go the other way, and any other number is partial, partial. So how do we know which one is which? This one right here basically is not picking up any phase from reflections, nor is this relative to each other. And so totally in phase basically means we're going to end up, essentially these diagrams are a little misleading. You have a actual splitter like this, and reflection and transmission is happening off of this back face. So if it's reflecting off of this, you're going from low to high. If it's reflecting off of this from this direction, you're going from high to low, and that introduces extra phase shift. So essentially, this right here, you'd have extra phase shift introduced by this beam. And so if they're out of phase by pi, this extra phase shift kind of nullifies that. And so you get a beam going this way. And if they're in phase, beam will go this way. Okay, this is what's sometimes called a Mach-Zehnder interferometer. Now you can modify it a little bit by, for example, having your beam splitter, let's put this down here, having a beam splitter down here, let's say. So now your beam comes in, interacts, goes off this way, goes off this way, and then maybe you put a mirror here as before. So this would be like M1, this would be BS1, this is BS2. Now instead of sending directly to the beam splitter, so let's put our beam splitter right over here again. Instead of sending directly to this with both arms, we'll send directly to it from this arm. But this arm, we're going to actually put a mirror, a mirror, a mirror, and a mirror, and then a mirror to send. So the path that this thing takes basically is this little zigzag like so. Okay. So obviously these two paths are not the same length. Now let's say for added interest, let's say that we put this on a little translation stage so that this pair of mirrors can be moved back or forward. Well, that changes the relative path length and therefore changes how much gets reflected and how much gets transmitted. Similarly, I could put like a gas tube into this beam line and fill it with gas or remove the gas, and that changes the effective path length as well. Could heat the gas, any of that stuff. Another style of interferometer would look like this. So I have, once again, my beam splitter. This time I send my laser into my beam splitter, and again I get some reflection, and again I get some transmission. But this time I simply put one mirror here that retroreflects. We'll call this one M1. I put another mirror here that also retroreflects. We'll call that M2. And for example, M2 might be on a stage that's movable, or it may have like a gas chamber or something like that onto it. The beams will reflect like this and like this. And essentially, you can either get a beam coming this way or you can get a beam coming back this way. And so maybe I put a little screen down here. On the screen, for an idealized beam that doesn't have any spatial extent, I either get a bright spot or I get a dark spot. So idealized, I basically get this, or I get nothing. Okay, so that's idealized. Really, what I will end up getting is something that looks more like this. So I get a series of bright and dark fringes that are ring-shaped. So these are my bright and my dark fringes. And I could say or. The or basically just means I flip where bright and dark is. And as it turns out, if I put the screen over here, whatever occurs on this screen over here will be the inverse of whatever is on this one. So if I have this bright spot, then I'll get a dark over here. If I have this pattern, then I'll have a dark inner fringe, then a bright, then a dark, then a bright, then a dark, as opposed to bright, dark, bright, dark, bright. So this is what's called Michelson interferometer, or Michelson interferometer. One other piece of technology is what's called the Fabry-Perot etalon. Essentially, it's a pair of mirrors that you insert into one or both arms. And what that does for you is it sort of like amplifies any effects that are detected. So essentially what we're expecting here is that we have our two beams, and so this beam is incident, it reflects, it hits the mirror, it comes back, it passes through. If this path length right here has value L1, then this beam will have traveled L1 apart from the other beam, and this beam will have traveled L2 apart. All right, and so that's what these two terms are. Now, with that said, this beam, again, is reflecting from the back face, hitting a mirror, and then passing through, no phase shift. This beam is passing through and then reflecting from what is effectively the front face on the other side. That introduces an extra phase shift of pi. It basically means that I need to have an extra term in here, so plus pi. Now E1 and E2 are equal to each other for a 50-50 beam splitter. They're both 1 over root 2 times the incident E. So that part for 50-50, what we would have is E1 equals E2 equals 1 over square root 2 of E incident. Okay. Now these two, basically when they recombine, you can add these cosine terms using your law of cosines, or your law of sum of cosines, whatever you want to call it. What you'll end up getting is essentially E total is proportional to the cosine of 2 times k times delta L plus pi or minus pi, whichever you want to do. So basically, like subtract L1 from L2, you have also this plus pi term. And so if this right here is, if this is collectively equals 0, pi, 2 pi, 3 pi, etc., then you end up with really a bright spot on your screen. And then if it's half pi's, then you get a dark spot. And that's how interferometry works.